Hello. Today we'll be talking about probability, but this time talking about it with biased outcomes and how does that change things. And so you might remember we say, okay, if we have this is an important if. So if all outcomes are equally likely, then we can say that we have the probability is of an event happening is well, that's just the cardinality of this event, like what are all the outcomes in this event over all the outcomes we have in the sample space. And so, for example, if suppose we're going to flip a coin, and suppose we have a coin that we call fair, and so in other words, the probability of getting a heads is the same thing as the probability of getting tails is just 1/2. And what if we said we'll flip this coin, we'll flip it 10 times? And I asked you, what's the probability we get 9 heads and then a tail on the 10th flip? And so kind of we can just use this same idea. So, well, that's the same thing as the cardinality of this event here, this like 9 heads and a tail on the first 9 flips, then a tail the 10th flip over, well, what's all possible things we have? Let's like 10 flips. All possible events here. So, well, each flip we could have either heads or tails, right? And so if you think about all possible flips, you get 2 for the first, 2 for the second flip, and so forth, all the way to get a ton of these. We get 2 to the 10th for these flips, and then thinking about, well, what would it mean to have 9 heads and then tails on the 10th flip? Well, that just means we have kind of all these heads showing up, and then we have a tails, the last thing. And so actually with this, we only really ever have one possibility here, right? Because I'm saying, okay, well, I have to have a head in the first place. I have to have a head in second place. I never can have, I have to have tail in last place. I never have any opportunity to vary anything. So in this case, I actually would say I only have one possible outcome in this event. And so then I'd say, okay, I have 1 over 2 to the 10th is my probability. I actually could do this. You might look, oh, this actually looks kind of similar to geometric distribution. And if kind of remember, geometric distribution is kind of saying, we'll keep going until we succeed. So if first we don't succeed, try again, right? And so we'll say we have a probability that we get 9 failures where we're trying to get some tails, and so we fail when we get heads, and we succeed on the 10th flip. And so in this case, geometric, we're saying, okay, that's the the probability of that we fail, which is 1/2. It's the 9th. We fail 9 times times 1/2 to the first because we succeed on that last 10th time, and so we get 1 over or 1/2 to the 10th, which is the same thing as 1 over 2 to the 10th. But now let's think about, well, what if we change things? So this is the same. Okay, we're saying if all outcomes are equally likely, we have this. But what if I told you my coin is not fair? What if we said we have some evil coin here where the probability of getting heads is actually 9/10, and then the probability of getting a tail is only 1/10. And so here, okay, well, I think, yeah, well, this probability should increase, right? If I have getting a lot more heads, the probability of heads increased, so I think this probability should increase. But if I kind of do the same approach here of, okay, the event cardinality of the event over the cardinality of the sample space, well, actually, I still only have one outcome where I have 9 heads and then 1 tail, right? Because I'm still I still have to get 9 heads in a row, and then I get 1 tail as the last thing. And so I actually haven't changed the number of outcomes. The number of outcomes is still 1 possibility, and I have 2 to the 10th possibilities as my total sample space. But the problem is that my probability has changed now. So it's not the case that all events are equally likely. This event is actually, it's a little bit, maybe more likely than some other event where I said, okay, what if we got 9 tails and then a head? Well, if the coin flips were if we had 1/2, then this would be the same 1/2 probability each. We have this would be the same probability as this event here, but because we've made the coin biased, then actually this event getting the heads is more likely. And so to capture that, we can think about, okay, well, let's apply. We cannot do this approach anymore. We can't say the probability of these flips is like or of some event. Maybe we'll call it F. We can't say the probability of F is equal to the equal to the cardinality of F over sample space. If we know that, yeah, we have biased outcomes. We cannot do this anymore. So how can we resolve this problem? Well, we'll go back to our old friend, the geometric distribution. And so we can say, well, we get 9 failures. Well, now the probability of a failure is, so yeah, we fail when we get heads. So that's okay. The probability of failure is 9/10. And the probability we succeed getting tails is 1/10. And so we'd say, well, I know I got, if I'm getting 9 heads and then a tail, then I know I'm getting 9 failures and then 1 success. So then I get, yeah, this probability here, which I can actually leave it in this form of 9/10 to the 9th over 1/10 to the 1st. And so, yeah, so I've saying I've failed 9 times, and then here I succeed 1 time. So I can also think about this in terms of, well, what if I vary this problem a little bit and said, actually, I'm not saying the last thing's a tail. I'm just saying I get like 1 tail total. Well, if we're in the fair case, then I could kind of change this to be sample space stay the same, right? I still have 2 to the 10 possible flips because I have 2 possibilities each time. But now I can think about, well, actually this tail, it could be here as one possibility, but maybe the tail is here, or maybe it's there or here. And so I actually have 10 possibilities for where the tail could be. And so you can think about this as 10, or I can choose 1 because I'm choosing where the tail is out of like one ordered choice out of 10 options. And so I get then 10 over to the 10th, or I can do this with use the binomial distribution. And we're saying we want to have 1 tail, 9 heads. We don't really care about the order at all. And so the probability of this would be, well, I'll have my n is equal to 10 here. And I'm choosing 1 thing. And then so this would be my k. And then I'm saying, okay, the probability of getting these like 9 heads, well, that would mean I have 1/2 to the 9th, and then 1/2 to the 1st. If I then add some bias, like I can't apply this formula again because again, like getting 9 heads and a tail somewhere, not necessarily last place. Well, this, if we bias the coin to be 9/10 probability heads and 1/10 probability tails, well, this is actually more likely than getting 9 tails and 1 head somewhere. And so, but this approach will give us the same probability either way. If we say if we think it's equally likely, but they're actually biased. And so we have to use binomial here, or should use binomial here. And so we could say, okay, let's 10 choose 1. Here we get 9 heads, and so we get 9/10 to the 9th, and then we get 1 tail is 1/10 to the 1st. And so this is us choosing, okay, like where do I want the where the tail is, and then 9/10 to the 9th is saying, okay, the probability of getting like these 9 heads, and then here's the probability of 1 tail. And I could also equivalently say, I could say if I wanted to 10 to the 9th instead, which is equivalent, and that'd be choosing where the heads are. And so if I choose the 10th, you might remember that, okay, it's the case that 10 to the 1st is equal to 10 to the 9th. We have n to the k is equal to n to the n minus k. And you can work out the logic here of n factorial over k to the n minus k, you find that is the same thing. If we do this here, yeah. Yeah. So you get like end up getting the same answer there. Oh, sorry, it should be n minus k. Yeah, but these work out to be like the same thing numerically, and so yeah, we can say either way we're working to count this, and so yeah, I guess kind of to recap, if we have biased outcomes, we can no longer use this formula of we have the expected cardinality of the event space over the cardinality of sample space. So we can use this if we have all outcomes equally likely. If not, we have to use the kind of underlying distribution. And so in one case we use the binomial, in one case we use geometric, but and you kind of think about, okay, like what is this? How can I compute this without using the formula if it is biased? And so if it's not biased, then I encourage you to use this formula, or maybe to use, you can still use binomial if you want to, or geometric as needed, or other distributions. But yeah, that should be a good primer on probability. And best of luck as you study for the exam. Take care.